Have you ever stopped to think about what's really happening when you boil a kettle? I mean, it seems so simple, right? But underneath the surface, there's this incredible story of energy unfolding at a molecular level. Today, we're going to go on that exact journey. We'll follow a single piece of ice as we pump it full of energy and watch it transform step by step all the way into superheated steam.
But to get us started, here's a little brain teaser for you. Imagine you've got a tiny teaspoon of water boiling away at 100 degrees Celsius. And next to it, you've got a big bowl of water that's just kind of lukewarm. Which one do you think is packing more total energy? The answer might not be what you expect, and it gets right to the heart of what we're talking about today.
And the answer is the large bowl of lukewarm water. Yeah, I know it sounds totally backward, doesn't it? But this is because we have to pull apart two really important ideas: temperature and internal energy. See, temperature is just a measure of the average speed of the particles, how fast they're all jiggling around. So yeah, the particles in the teaspoon are moving way faster. But internal energy, that's the total energy of all the particles put together. The bowl has so many more particles that even though they're slower on average, their combined energy is way, way higher. It's really a case of quantity over speed.
So let's just put in a nice clean definition on that. Internal energy is made of two parts. You've got kinetic energy, that's the movement and jiggling we just talked about, and then you have potential energy, which is the energy that's kind of locked away in the bonds holding all those particles together. And trust me, this potential energy part is going to become super important in just a minute.
Okay, let's start our journey. We begin with a solid block of ice, nice and cold, way below freezing. Now, as we start adding heat, we're basically handing that energy over to the water molecules. They can't really move around, they're locked in a crystal, but they start to vibrate in place, faster and faster and faster. This increase in vibration, this kinetic energy, is what we actually measure as a rise in temperature.
So, how much energy does this take? Well, that all depends on something called specific heat capacity. It sounds complicated, but it's really just a number that tells you how much energy you need to shove into 1 kilogram of something to make its temperature go up by just 1 degree Celsius. You can think of it as a substance's thermal stubbornness.
And this value is wildly different for different materials. I mean, look at lead. It only takes 129 joules to heat a kilogram by 1 degree. Super easy. Brick takes a bit more work, 840, but then you get to water. 4,200 joules. Water has an insanely high specific heat capacity. It really fights you on changing its temperature.
So what does this mean in the real world? Well, a low value, like leads, means it heats up really fast and it cools down just as fast. You don't put much energy in, but it also doesn't hold on to that heat for long at all.
But a high value? That means the material is like a fantastic energy sponge. It's exactly why we use bricks and storage heaters. They soak up energy all night and then slowly release it all day. And it's why we use water in our radiators. It can carry a ton of thermal energy around your house.
Okay, let's get back to our block of ice. We've been heating it up, and the temperature has been climbing and climbing, heading straight for 0 degrees. But the moment it hits 0, something weird happens. The temperature just stops. It gets stuck right there at 0 degrees Celsius, even though we're still pumping heat into it. This is the first big plateau on our journey.
And this is the central mystery, right? We know energy can't just disappear. So if it's not making the particles vibrate faster, if the thermometer isn't moving, what is all that energy actually doing? Where is it going? And here's the secret. The energy has a new job. It's not going into kinetic energy anymore. It's being funneled into the potential energy store. It's being used to physically attack and break the rigid bonds of that ice crystal, snapping them apart so the molecules can finally break free and slide past each other. It's turning the solid into a liquid. This hidden energy has a special name: specific latent heat. Latent literally means hidden, which is perfect because it doesn't show up on a thermometer. The specific latent heat of fusion is the precise amount of energy it takes to melt 1 kilogram of a substance.
And for water, that number is staggering. It takes 334,000 joules of energy just to melt 1 kilogram of ice that's already at 0 degrees. To give you some perspective, that's enough energy to lift that same kilogram of water more than 34 kilometers straight up into the sky.
So our ice is melted. We've now got a puddle of water at 0 degrees Celsius. We keep adding energy, and just like before, the temperature starts to climb again. The water molecules are zipping around faster and faster. 10 degrees, 50, 90, until we hit 100 degrees Celsius. And guess what happens? You got it, we hit our second plateau.
The temperature gets stuck all over again. This time, we're dealing with a second type of latent heat, the specific latent heat of vaporization. This is the energy needed to break the last of the bonds holding the water molecules together as a liquid, letting them escape completely and become a gas, what we call steam. Now, let's just put these two values side by side. Melting the ice took a huge 334 kilojoules per kilogram, but turning that water into steam, that takes an absolutely colossal 2,260 kilojoules per kilogram. It takes almost 7 times more energy to boil water than it does to melt ice. That's just incredible.
Okay, we've looked at all the individual steps: heating the solid, melting it, heating the liquid, boiling it. So now let's zoom out and put it all together to see the full, complete energy journey from beginning to end.
And here it is, our whole trip in one simple graph. You can so clearly see the two climbs where we're adding energy and the temperature is rising, and then you see the two perfectly flat plateaus where all that energy is going into changing the state, first melting, then boiling. And just look how much longer the boiling plateau is. That just shows you how much more energy that step takes.
Okay, time to put this knowledge to work. Let's imagine we have half a kilogram of pretty hot water, say at 80 degrees. And our goal is to turn it into superheated steam at 110 degrees. To figure this out, we have to calculate the energy needed for 3 separate stages of the process.
So here's our game plan. Step 1. We'll use the specific heat capacity of water to figure out the energy needed to get it from 80 up to the boiling point of 100 degrees. Step 2, we use the latent heat of vaporization to find the energy needed to boil all of it. Step 3, we'll use the specific heat capacity of steam to heat it up that last little bit from 100 to 110. And finally, step 4, we just add them all up.
All right, let's crunch the numbers. Heating the water up to boiling takes 42,000 joules, no problem. Then, turning it all into steam at that temperature takes a massive 1,130,000 joules. And finally, heating up the resulting steam takes another 9,295 joules.
And the grand total comes to over 1.18 million joules. But here's the crazy part. Look at those numbers again. Almost 96% of the total energy we had to put in was used just for that change of state, that hidden latent heat of vaporization. The actual temperature changes were just a tiny drop in the bucket.
So, if you take away one thing from this whole journey, let it be this. The energy locked away in the bonds that hold molecules together is absolutely immense. And breaking those bonds to change a substance's state, that often takes way more energy than just making something hotter. That's the whole ballgame.
And that leaves us with a final, kind of mind-blowing thought to chew on. We just saw that turning about half a liter of water into steam takes over 1 million joules of energy. A single thunderstorm can hold hundreds of thousands of tons of water vapor. So what does that tell you about the truly colossal, almost unimaginable amount of energy that gets released when all that vapor condenses back into rain? It's definitely something to think about next time you see a storm rolling in.